Hello folks, and welcome to this odds and ends lessons of nomenclature. In this lesson we're going to be covering two shorter topics, acids and hydrates. Now acids are probably going to be the topic that comes out quite a bit more than the hydrates themselves, and the thing about acids is that you have to be very careful because an acid is only an acid if it's in water. So if this chemical is not dissolved in water, it is not an acid, and so therefore you're not going to name it as an acid. Now, when you do dissolve it in water, the way that you know this is because of its state. It will tell you its state and it will say that it is aqueous. If it does not specifically say that it is aqueous, or it does not say that it is dissolved in water in solution, then you can assume that it is anhydrous. Anhydrous, the an refers to no and the hydrous refers to water, so anhydrous means no water. If you have anything that is anhydrous and it's supposed to be an acid, you just name it as if it were any other binary compound. So in this case we have hydrogen and we have chlorine. It's simple binary, so you're going to take the name of the first one, you're going to take the name of the second one, and change the ending into IDE. And that's it. That's your typical naming. However, once you see that you have that AQ, it's in water, you do change the naming a bit. You are going to name it as an acid, and you're going to, if it's a binary acid, so if there are only two elements, hydrogen and that one other thing, if it is binary, you're going to add the prefix of hydro, and then you're going to put the name of that second element and change the ending into IC. And so HClAQ is hydrochloric acid. So, two things. Make sure that it is in water, otherwise you're going to treat it like any other binary compound. If it is a binary acid, so you only have two elements, hydrogen and that one other one, then you're going to use this hydroic acid convention. Now this world is wonderful and it is also complicated, and so of course you're not only going to have binary acids, you can also have acids with polyatomic ions. Those acids we refer to as oxyacids because they have the oxyanions. And this is the method that you're going to use when you have those oxyanions and you have the oxygen variations. Once again, as a reminder, if it's an acid, it's going to be dissolved in water, so this naming only happens when it is dissolved in water. So you have your main oxyacid, so that's the one where your polyatomic ion is the 8 version. So when you have that, you're going to go from chlorate, change the ending to ic, and then you're going to add the name or the word acid to the end of it. There is a space between the chloric and the acid, and that space is going to exist for all of your compounds. Now, if you have your oxygen variations, then the name is going to change a little bit. So when we take out one oxygen, you have your ClO2, and this is going to be aqueous because we're naming acids. Now you're still going to have one hydrogen because your chlorite ion has a -1 charge. -1, +1, you're going to have one of each. So this is your chlorite ion. So if you have the ite polyatomic ion, then the name becomes chlorous acid. Now hopefully you have noticed by now the big difference between your binary acids and your oxyacids is your binary acid has that prefix of hydro in it, your oxyacids do not. And so that's going to be the big way to tell, based on the name itself, whether it's a binary acid or whether you're going to have to bring out those polyatomic ions. Now, when you have your hypoite ions, so in this case we're going to have your ClO with one oxygen. If you have your hypoite ion, and that is an acid, then what you do to the name is you add hypo to the beginning, You keep the ending as us, and then you add the acid on the end. Hopefully you'll notice that there are some parallels to how these prefixes and suffixes are changing depending on whether you've lost or gained your oxygens and so on and so forth. So hopefully you can use these patterns, see what those connections are, and use them to your advantage. Now, when you add an oxygen, then you're going to add per to the very end, to the very beginning. You're going to add the per prefix. It's an acid, so we're going to add that hydrogen. We only need one for this particular one. And then the name is going to be perchloric acid. So there you go. That's how you change the names of your oxyacids. Now the number of hydrogens is going to depend on the charge of your polyatomic ion, however many you need to make that overall charge to be 0, because these acids are compounds after all. Now hydrates aren't going to show up a whole bunch, but they do exist, and you will see a lot of chemicals being sold as hydrates because that's just how they exist. And you'll also see them in this course at very, very specific times. What a hydrate is it's basically an ionic compound that in its whole crystal structure, water molecules have also gotten mixed up in there. And funnily enough, like the ionic compounds that have very, very specific ratios, the ratio at which you have these water molecules is also going to be very fixed. You always have the same sort of ratio when it comes to these hydrates. The naming actually isn't all that difficult. You just have to remember what each part means. And basically, as I mentioned, this is an ionic compound that has some water. So first thing you're going to do is you're going to name the ionic compound. Then, because it has water in the name, you're going to add hydrate to the very end. And then you're going to say how many water molecules there are. So what's that ratio between your ionic compound and your water? And you're going to indicate that ratio using a prefix like mono, di, tri, and so on and so forth. So here's an example of a hydrate. We have this ionic compound, and you have a dot separating that and the water bit, the hydrate bit. You have your waters, and it says that there are 6 waters in there. So you're going to name the ionic compound itself. So here we have cobalt to chloride. And there is a space. It's going to be a hydrate. There are 6 waters in there, so this is hexahydrate. One of the key mistakes that I usually see when it comes to this nomenclature is when students see this hydrate, they think of it as hydrogen and not water. Remember, hydrating yourself, people keep on saying in real life, like, make sure you're keeping hydrated. Means make sure you're drinking your water. And so that hydrate is always going to refer to water. If it were hydrogen, it would be hydride. All right, so that's it for this lesson. I'll see you next time.